Hi everyone, so hope you're all doing well and hope you're all ready for the new academic year, ready to go again. So I found this question, and this is question 5 from the Edexcel 2021 mechanics paper for A-level maths. And this is the last question on that mechanics paper. And it's quite a tough one, so I think it'd be a good idea to run through this question today. So that's what we're going to do in today's video.
But before we get into today's video, please do make sure you do click like and click subscribe. Click that like button, click subscribe. It really helps me out and it's free. It doesn't cost you anything and it takes you less than a second. So please do click those buttons and we'll get into today's video now.
So this question here, we've got at time t seconds, a particle p has a velocity v, where the velocity is given by this vector here. So 3t to the power of a half in the I direction, minus 2t in the j direction. So we got a vector. We want to find the acceleration of the particle at time t seconds. So obviously, I guess the first thing to remember is that acceleration is a vector. So the final answer will be a vector. So we've got a velocity, we've got an expression for velocity, and it's variable acceleration as well. So why is this variable acceleration? Because the velocity is a function of time. So the velocity, the speed of the particle, essentially, depends on time, and so therefore the acceleration is going to be this variable acceleration. It won't be a constant acceleration. So how do we go from velocity to acceleration? Well, we differentiate. So our acceleration is going to be the derivative of velocity with respect to time. And if we differentiate both the I component and the j component, that will give us our acceleration. So we're going to differentiate with respect to time our I component, and then do the same thing with our j component. So minus sign, and then differentiate with respect to t, this 2t in the j direction. So when we differentiate this 3t to the power of half, bring the power to the front, take away 1 from the power, we get 3 times a half, and then times by t to the negative a half. 1 take away a half, half take away 1 is negative half, and this is all in our I direction. And then in our j direction, take away sign, derivative of 2t is 2, so 2j. So then what we get is you get 3 times a half, which is 3 over 2, times by t to the negative half in the I direction, and then take away 2j, obviously in the j direction. So that would be our acceleration there. And again, acceleration is a vector, so our final answer will be a vector. Now, if you had a question which asks you for the magnitude of acceleration, then you would use Pythagoras to find the magnitude. So part B, to find the value of t at the instant when p is moving in the direction I minus j. Okay, right. So we want the particle to be moving in the direction I minus j. Okay, so let's just think about what this means. So I minus j, what direction is this? So remember, your I component is in this direction, your j component is in this direction. So a vector or a particle moving in the direction I minus j. So I is going to look like this. Minus j is going to look like this. So the opposite of this j there, that's going to be minus j. So a vector, and I'll do this in a different color. Let's do it red. So this vector going from, try and do that again, just make it look neater. So I minus j is going to be this vector there, just by using our factor vectors. That's going to be the I minus j vector. So we want the particle to be traveling in this direction. So in other words, we want this particle to be traveling like in a kind of like a 45 degree, obviously that's 45 degrees there, kind of like a 45 degree downwards trajectory. So that means that we need the velocity. So we need velocity to be equal to this I minus j vector times by a scalar number. So for example, just call it k. So k times by I minus j. So why is that? So obviously, if your speed is a multiple of this I minus j vector, then you're traveling in this I minus j vector direction. So to travel in a direction of a vector, your speed must be in the direction of that vector. So basically, if we want to travel in the I minus j direction, then your velocity needs to be I minus j. I mean, it could be exactly I minus j, or it could be I minus j times 2, it could be I minus j times 3 or 4.5, whatever you like. So we need a velocity of k times I minus j, and let's be very specific, where k is a positive number. Could be any number, could be half, could be 1.78, whatever it is. We just need to travel in this direction, and the k basically tells us how fast we're going, but we're traveling in this I minus j direction. Okay, so that's what we need. Now, okay, so we know that's our velocity there, because that's the velocity of the particle. So let's just copy out this velocity again. So we've got a record of this. So velocity is 3t to the half. I'm just going to put it in brackets just to help me out, basically. 3t to the half times in the I direction, sorry. And then we got minus 2t in the j direction. Okay, so what we need then is we need this 3t to the power of a half to be equal to this k number that we came up with up here. So what we need is we need this 3t to the half to be equal to this with this 2t here, because remember we got the minus sign there already accounted for. In fact, what I'm going to do is actually just expand the brackets. So we've got ki that minus kj that. Okay, so what we want is we need 3t to the power of a half to be equal to k. So let's just color code this to make this very clear. We want the velocity, this velocity, to be the same as this velocity. So we need the k to be equal to this 3t to the half. And we also need, obviously, this k over there to be the same as this here. So we need 3t to the half to be equal to k to be also equal to 2t as well. So that's what we need. So what we can do then is we can say, well, therefore, 3t to the half is equal to 2t. And then what we can do now is actually just square both sides, because then we get rid of this power of a half here. So let's square both sides. And if we do that, we will get 9t is equal to 4t squared. So square the 3 to get 9, square the t to the half to get t, square the 2 to get 4, square the t to get t squared. So we get kind of like a quadratic now. So we get, if we take away 9t from both sides, we get 4t squared, take away 9t is equal to 0. And then we can factorize out a t. So factorize out a t equal to 0. We got 4t, then take away 9. So we're going to get two possible solutions. So either the t there is equal to 0, or this 4t take away 9 is equal to 0. And so therefore 4t is equal to 9. And so therefore t is equal to 9 over 4. Now if we just go back to the question, so we got two solutions there. Now obviously we're told in the question that t has to be bigger than 0. So this t equals 0 solution is not acceptable. So that one is not acceptable. However, this one there is, so that's our answer there. So t is equal to 9 over 4. Okay, so that's part B. The next part then, so at time t seconds, where t is greater than 0 again, the position vector of p relative to the fixed origin O is r meters. So we got this vector, position vector r. When t is 1, r is equal to negative j. So we want to find an expression for r in terms of t. Okay, so we know that we've got a velocity here. We've got this velocity vector there. So how do we go from velocity to position? So remember, position is basically your displacement. how do we go from velocity to displacement? We integrate velocity with respect to time. So let's just do this here. So part C, so our position vector is the integral of our velocity vector with respect to time. Let's just copy out our velocity vector again. So our velocity vector was 3t to the half in the I direction, and then take away 2t in the j direction. And we're integrating this with respect to t. Okay, so the way we integrate vectors, I mean, it's just the same as integrating anything else. You integrate the two components individually. So we're going to integrate the I component, so this component, and then we're going to integrate the j component there. Okay, so integrating the I component, this 3t to the power of a half, how would you integrate that? Well, you add 1 to the power of the t variable, divide by the new power. So you're going to get 3t, add 1 to the power, you'll get a half plus 1, which is 1.5, so 3 over 2, and then divide by that new power of 3 over 2. Okay, so that's going to be our I component, and then we're going to have we're going to integrate this negative 2t. So add 1 to the power, divide by the new power is going to be negative 2t squared, divide by the new power, divide by 2 in the j direction. However, we're not done with the integration. So remember, we're doing indefinite integration. We've got no limits on the integral. So we're going to have to add constants. So we're going to have to add a constant. And really what I'm actually going to do, I'm actually going to add the constants within the two components. So, sorry, let me just rub this out here. What I'm going to do is I'm going to add a C1 here. So I'll call this constant number 1 there, and that's in our I direction. And what I'm going to do here is add a C2 here, a second constant in our J direction, a second constant there. Because remember, when we do indefinite integration without limits, there could be an extra constant that we need to add on. So we just need to add on the C's in both directions because we're integrating both directions, the components of both directions. So, okay, let's just simplify our numbers here, just make this nicer. So 3 divided by 1.5, well, that's going to be 2. 2t to the power 3 over 2, and then plus this C1 in our I direction. And then take away, well, 2 over 2 is just 1. So we get t squared plus C2 in our j direction. Okay, so now then, this is where we've got to use the data to try and work out what this C1 and C2 is. So let's look at this data here. So this piece of information helps us out. So when t is 1, r is equal to negative j. Okay, so when t is equal to 1, let's plug that into our formula for r. So r is going to be equal to, so plug t equals 1. So 2 times 1 to the power of 1.5, 1 to the power of 1.5 is 1. 2 times 1 is 2. So we're going to get 2 plus C1 in our I direction. And then take away t squared. Well, t is 1. 1 squared is 1. 1 plus C2 in our J direction. And we're told in the question that when t is 1 second, the r is equal to negative j. So in other words, 0i minus j. And in fact, I'm just going to put a number 1 there just to really make this clear. So negative j is the same as 0 in the I direction and minus 1 in the j direction. That's what we've got there. So we can see that if this line there is equal to this line there, then we've got 2 equations from this. So therefore, 2 plus C1 is equal to 0 because we want this to be equal to that. And also, just rub out the circles here. And also this there, this 1 plus C2 must be equal to the 1 there. So we've got 2 equations that we can extract just by matching our coefficients. So we've got 2 plus C1 equals 0 from the first part. And actually what we can tell from here is that C1 is equal to minus 2. And then from our second equation, 1 plus C2 is equal to 1. From there, we can tell that C2 is actually equal to 0. Take away 1 from both sides, you get C2 equals 0. So we know that C1 is minus 2, C2 is 1. So the question, let's just go back to the question to remind ourselves. So the question is, find an expression for r in terms of t. Find the position vector in terms of the variable t. So we've pretty much done, I mean, we've done the hard work here. We've done the hard integration there. But now we've calculated C1, we've calculated C2. We know that C1 is -2, and we know that C2 is, sorry, I made an error here. Sorry, this is 0. Sorry, my bad, 0. C2 is 0. It's nothing. So C1 is -2, and C2 is 0. So we can just plug it into our result. So therefore, our position vector R is going to be equal to 2t to the power 3 over 2. So 2t to the power of 3 over 2. And then plus our C plus our C1, which is -2. So -2 in our I direction. And then in our J direction, we got negative t squared plus C2, which is 0. So negative t squared J. T squared J. So there we go. That's our position vector, and that's part C done. Sorry, just make the line look a bit more straight instead of a diagonal line like that. So that's part C. And then we got one more part to the question. So part D. So we want to find the exact distance of P from the origin O. So remember, O is the origin. So if you've got like a graph like this, you've got a particle traveling along your X and Y axis, so doing some random stuff like that. You've got your origin, which is in the middle. So that's what it means in these questions. Your O is your origin. So find the exact distance of P from O at the instant when P is moving with a speed of 10 meters per second. Right, so we need the particle to have a speed of 10 meters meters per second. So remember that, sorry, let me get rid of that equal sign there. So we've got a speed which is 10 meters per second. So remember, speed is the magnitude of velocity. So speed is essentially this, the magnitude of the velocity vector. So how do you find the magnitude of vectors? Well, use Pythagoras of the two components. So we've got a velocity, again, the same velocity as before, this velocity at the top here, 3t to the half in the I direction and -2t in the rj direction. So what we want to do is we want to find the magnitude of this vector, so 3t to the half in the I direction, -2t in the j direction. So we've got, again, this 3t to the half in the I component, -2t in the j component. So we want to do Pythagoras. So the speed, so remember Pythagoras, a squared plus b squared is c squared. So that means our c, which is essentially our speed, is the square root of this I component squared plus rj component squared. So it's going to be the square root. So speed is the square root of 3t to the half all squared, and then plus this j component -2t all squared. Technically, we should include the minus sign. I mean, when you do Pythagoras, it doesn't matter whether you include the minus sign or not. But because obviously when you square a negative, you get a positive. But technically, we'll just include the minus sign. So just to diagrammatically explain this, we've got 3t to the half in our I direction. We've got this -2t in our j direction. So the speed is the magnitude of this. So the hypotenuse essentially. So to get our hypotenuse, our speed is going to be equal to, again, this square root of this I component squared plus this j component squared. So that's kind of a diagrammatic explanation of why we're doing Pythagoras here. Okay, so what we're going to do then, just simplify what we have here. So we've got the square root of 3t to the half squared. 3 squared is 9. T to the half squared is t, because t to the half times t to the half is t. And then -2 squared is 4, so plus 4. And then t squared. Okay, so we've got that, and we know that this is equal to 10. So just put like an equals 10 here to make that clear. So let's just square both sides to get rid of this square root, because this square root is kind of messing things up a little bit. So we've got 9t plus 4t squared is equal to 100. And then we can just rearrange this to make it look like a quadratic equal to 0. So 4t squared plus 9t minus 100 is equal to 0. So you've got this quadratic there. So we know that when the speed is 10 meters per second, we know that this equation must be satisfied for the time. Now, I guess we could try and factorize this. I'm gonna cheat. I'm not gonna be. I can't be bothered to factorize it or try to factorize it. I'm just gonna use my calculator. I mean, obviously you could use quadratic formula, but I'm gonna go to my calculator. I'm gonna go to the equation solver. Hopefully you guys know this, but if you have any questions, do drop a comment and I can try to help out. So you're gonna go to your calculator. We want a quadratic polynomial. Our A is 4, our B is 9, and our C is negative 100. I'm just going to put these numbers in my calculator. 4, 9. Sorry, I forgot the minus sign. Sorry, minus sign, negative 100, minus 100. Plug that all in, and I get two solutions. So from calculator, I get that T is 4, or T is negative 6 point. Is that, yeah, 6.25. Okay, right. So obviously you can't have negative time in A-level maths. So this one is nonsense. But this positive value there works. So we know, so the conclusion we can draw from this is that the speed is 10 seconds after 4 seconds. Sorry, the speed is 10 meters per second after 4 seconds. So what we can say is that when no, my pen started to freeze for some reason. Sorry, give me 1 second. There we go. It's back now. Sorry. Right. So when t is 4 seconds, so when t equals 4, the speed is equal to 10 meters per second. So that's the conclusion we can draw from that. Now, how is that going to help us answer the question? So let's go back to the question. So we want to find the exact distance of P from the origin at the instant when P is moving at a speed of 10 meters per second. Right, so we know the position vector, because that's what we did in part C. With a lot of these questions, there's a reason why we had to do part A, part B, part C, because it helps us out with future parts. So we know we want to find a distance. So distance is, essentially the same thing as position, displacement. When we're talking about positions, distances, displacements, we're kind of meaning the same thing, really. Obviously, distance is a scalar, position, displacement, they're vectors instead. But we know the displacement, we know the position because we did that in part C. So let's just copy out our position vector again, because this position, not that one there, this one here, this position there, that tells us the position on our XY axis after t seconds, right? So I'm just going to copy out our position again. So we know that the position, of our particle, so of particle P is, so it's this vector here, so this R equal to 2t to the power 3 over 2. And then it was a minus 2, wasn't it? Yeah, minus 2 in our I direction. And then it was, what was it in the J direction? Minus t squared in our J direction. So minus t squared in our J direction. But we know, so we want to find the distance from the origin when the speed is 10 meters per second. But we know that when the speed is 10 meters per second, we know that the time is 4 seconds. So that means the position. So if we work out the position that we're at on the grid, so remember we've got this grid here, our particle's moving around like this, something like that, and we've got our stopwatch, we're measuring the time. 4 seconds later, the speed is 10 meters per second. So let's just say that 4 seconds later, we're there. Our particle here is on the grid. So remember, x-axis there, y-axis there. 4 seconds later, we'll just pretend we're here. The speed there is 10 meters per second. So let's find out the position 4 seconds later. So the position when t is 4, well, we're just going to plug that into our r vector, our position vector. So that's going to be 2 times by 4 to the power 3 over 2, take away 2 in our I direction, and then take away 4 squared in our J direction. So, okay, 4 to the power 1.5. So that's the same as square rooting 4 and then raising it to a power of 3. So that's going to be 2 and then times by 8, take away 2 in our I direction. And then obviously 4 times 4 is 16, 16J. So 2 times 8 is 16, take away 2 is 14, so 14I, and then minus 16J. Right, so we know our position vector 4 seconds later. So when the speed is 10 meters per second, when we're traveling at a 10 meter per second speed, it's taken us 4 seconds to do that. And we've just calculated that the position on our grid is 14i and minus 16j. So actually, let's just sketch this here. I mean, this is all nonsense here because actually it doesn't look anything like that. This is going to be our real position. So 14 on our x-axis, so 14 in the I direction, and minus 16 in our j direction, so minus 16 on the y-axis. So 4 seconds later, we've done some traveling, we've traveled around like this, and then 4 seconds later, we end up here. So that's where we end up 4 seconds later. But let's just go back to the question to remind ourselves. The question wants us to work out the distance of our particle from the origin when the speed is 10 meters per second, i.e. 4 seconds later. So we know that 4 seconds later, we are exactly there. This is our origin, that's our origin there. What is the distance from the origin to this position that we're at 4 seconds later? Well, you probably guessed it, it's going to be Pythagoras. It's another Pythagoras calculation. So you've got 16 there, you've got 14 there. Now, I know that this is negative 16 technically on our y-axis, but again, it doesn't matter whether you include the positive sign or the negative sign, because when you square a negative number, you get a positive number anyway. So that's that. So we've got origin there. We want to work out the distance. It's Pythagoras. So that's our distance there. Distance. So distance is going to be the square root of our 16 squared plus our 14 squared. I'll just do this in the calculator. 16 squared plus 14 squared. That's going to be the square root of 452. And then if we just square root that, what do we get? It's about 21.3 to 3 significant figures. 21.3 meters to 3 significant figures. And that is our distance. So we've answered the question. That's our distance from the origin 3 seconds later. Sorry, just check the question if they wanted it to a certain degree of accuracy. No. So with these questions, if they don't tell you a certain degree of accuracy, 3 significant figures is sorry, my bad, silly mistake. Find the exact distance, exact. Sorry, this is a bad mistake. Always happens, and always don't read the question. Let's get rid of this because this is not right. So remember, exact means you need to leave it as a third. So an exact number. Obviously, when you round numbers to decimal places, that's not an exact, correct, precise answer. So when you need to give an exact answer, you need to leave it in third form. So I guess this would be fine there, 452. Can we break it further into square number factors? 452. I'm just doing this on my calculator. 452 divided by 16. No. 452 divided by 4. Sorry, I've mistyped that. 452 divided by 4. Yeah, okay, yeah. So if you really wanted to, you could say the square root of 452 is the same as the square root of 4 times by 113, which is the same as the square root of 4 times square root of 113, which is 2 root 13. So if you wanted to, you could leave your answer like that, but this there is also acceptable as well. They're both the same thing. So that's our exact form answer, not the decimal form answer as I gave before. But any questions, do leave a comment and I'll get back to you. But hopefully that was helpful to go for a variable acceleration question. And remember, if you do have a velocity which is given as a non-linear expression in terms of t, then when you differentiate that, you're going to get an acceleration in terms of t. And an acceleration that depends on t, with t involved, is a variable acceleration because it's an acceleration that depends on time. So again, any questions, let me know. And thanks a lot for watching today's video.
If you are interested in having an online maths tutor for either A-level maths or GCSE maths, please do email me because I am available to help out. So my email is doctordifferentiation@gmail.com. So just drop me an email, just drop me some details about you, whether you're doing A-level maths, GCSE maths, and if there's any specific areas of maths that you need help with. So drop me an email or get your parents to drop me an email, and then we can discuss everything about price, etc. So drop me an email and we can get sessions booked in.